Hello viewers and my dear students. Welcome to session 2 on harmonic analysis. Here I am showing you a demo on harmonic analysis of a cantilever beam. This, as I told you just now, this is session 2. On session 1 I have done the basics of this, how it works, how the amplitude versus frequency graph is drawn and where all the peaks would appear. Everything I have told you in session 1. This is the session 2. Okay, and as you see here, this is the problem. The same problem holds good. I am doing the same problem, and if you take the same problem what we have done in modal analysis, the length is 1 meter, cross section 0.01 by 0.01, Poisson's ratio 0.27, density 7830, this is 200 GPa and all that. If you take, okay, you are getting the same answers here, and you are in fact you are verifying the answers obtained through modal analysis in harmonic analysis. That means, since I have told you 1 to 100 hertz here, they are given the problem as 1 to 100 hertz. In the 1 to 100 hertz, as you see here, you are having only two natural frequencies. 1 to 100 hertz, no, 8.3 and 52. That means only two peaks are going to obtain. Anyway, you will see now how exactly the things are done using Ansys. Okay, as usual, you start. Okay, as usual, you start preferences. Before that, as you know, file, clear, start new. These things you do. Okay, fit here, then file, change job name. Okay, change job name here. These things I have already done. This Gurudat harmonic you do, that means immediately you get a new log file. All whatever the graphic user interface, whatever you do, the procedure what we are adopting is GUI, that is graphic user interface. Whatever commands we give, all will be recorded in this Gurudat harmonic. Okay. Okay. Now you see here. Then after that, file, change title also you give, harmonic analysis. Of a cantilever beam. Harmonic analysis of cantilever beam, you just say. Then you say fit. Okay, now you got Gurudat harmonic analysis of cantilever beam, everything you got. Now you do in the same way. Preferences, first you go for structural. Okay, structural, you say okay. The initial part, everything is same as modal analysis, what we are doing. Okay, add, edit, delete. Add you do. Take beam element, beam 2 node 188 you take. Just say okay. You just say close. Okay. Then material properties you take. Material models you take. Structural, linear, elastic, isotropic, you take 2E11. Okay, that is 200 GPa, Newton per meter square, or 2E11. Okay, that you take, and Poisson's ratio they are given 0.27. You take the same thing. What we have done in modal analysis also, same thing you take. This is a material property you take, and density also you take. What we had given there was 7830 kilogram per meter cube. Okay, that also you take. Then material exit you do. Okay. Then once you do this, you take section, beam, common section you take. Once you take common section, it is 0.01. Correct? Breadth and height, same thing. 0.01. Please verify the drawing, that is the problem given. Breadth is also 0.01, height is also 0.01. The same dimensions. Whatever we have done in modal analysis, we take the same thing. In fact, this harmonic analysis will act as a verification for modal analysis. Whatever you get there, whatever the natural frequencies you get there, you get the same thing here also by a different method. That's all. Then you say that is 0.01, 0.01. Just say okay. Okay. Then once you do this beam, then go for modeling part. Modeling, create key points in active coordinate system. At 1, you know, you put the 0, 0, 0. Apply you do. Then you put 2. Then 1, 0, 0 you put. That means the key point 1 is here, key point 2 is here. The distance between 1 and 2 is 1 meter because we are all taking it in Newton meter square. Okay, Newton meter you take because we've entered E in Newton per meter square. The model should be in meter. Okay, then create lines, you create lines, straight line you create, join this and this. Okay, join this and this and say okay. Okay, once you create this line, then you go for meshing. Mesh attributes, no, default attributes only you take because there is only one element, there are no multiple elements and all that. It is beam only 88. Material, actually, if you see, it is only one material. Just say okay. Okay, default attributes only. But size controls you see here. Size controls you go, manual size, lines, picked lines. You pick this line. Okay, pick this line. Okay, say number of divisions you make 10 or 15 or 20, whatever you do. Okay, it won't matter much. Only thing is little increase in accuracy will be there. Now number of divisions 10 means 10 elements are created. Okay, I'll just say 10 elements are created. I'll just see. Okay, then you do mesh, lines, pick all or click this line. Just say okay. Now it has been created as, you see here, if you do this, list elements, if you see, you have 10 elements created. This is the verification. That means you are gone, you are in the right direction till this. Now 10 elements are created. Now be careful. Now loading and all that for this problem, don't do at the pre-process stage. What you have to do now is that don't load here. Now what you do is you go for solution here. Okay, loading should be done at the solution stage, not at the pre-processing stage. Now what we have done is meshing part is already completed. Now you go here, solution, analysis type, new analysis. Now previously modal. Now you take harmonic. Okay, take harmonic. Say okay. Okay, harmonic you take. Then your analysis options you go. Take the default values. Even here also default values. You just say okay. Okay. Now you apply define loads here under solution stage. Define loads. Apply structural displacement on key points. Here you know all degrees of freedom are arrested. All degrees of freedom you make it as 0. That means all degrees of freedom is arrested here. Okay. Now you see carefully. Then you have a force moment on key points. Here you give the force moment. Here, as you see here, I am applying a load of 100 newtons. 100 newtons in 1 second, 100 newtons 2 times in 1 second, 3 times in 1 second, 4 times in 1 second. That is 4 cycles per cycle, 4 cycles per second, 6 cycles per second. That is hertz, 5 hertz, 6 hertz, 7 hertz, and all that. That load will be applied here. This is okay. You take Fy. This you give minus 100 because in the problem it is there. It is in the negative y direction. That means this is the thing. Okay. Now this you should know the significance. This load of 100 newtons is applied at the end. That is harmonically. That means 1 time in 1 second. 2 times in 1 second, 3 times in 1 second, 4 times in 1 second. In that way, when you are varying this, in case it matches with the natural frequency, the peak should occur. That means up 1, 2, 3, 4 and 5, nothing will happen. Once you apply it 8 times per second, it matches with the almost natural frequency, one peak will occur. Then 8, 9, 10, 11, 10, nothing will happen. Again, once it becomes 52 times per second if you do, again another peak will occur. That is the beauty of this. This anyway we are going to see later on. Then load step options you go. This is very important. Okay, load step options, time and frequency and substeps you take. You see here, they have given harmonic range 0 to 100 only. This here, 0 to 200, if I give here, you can pick 3 picks. If I take 0 to 100, one natural frequency is 8.16, another is 51.15. That means 2 peaks only you can observe. This, they have given in the problem, harmonic frequency range is 0 to 100 only. You take 0 to 100. Number of substeps you take 100. You take anything. 100 means on x-axis it is 0, 1, 2, 3, 4 up to 100. If it is 50, it will be 2, 4, 6 in that way. 100 by 2. Okay. 2, 4, 6, 8 up to 100 it will be. Now 100 number of substeps 100 means it will be 1, 2, 3 up to 100. X-axis will be 1 to 100. Okay. Harmonic frequency range is 0 to 100. Harmonic frequency range 0 to 100. Very careful here. If I put 0 to 150 here, 143 something somewhere, you have another frequency. Okay, that means 3 peaks you would have seen. Now 0 to 100 means you can see only 2 peaks. One is 8.16, that is 8.2. Another is around 52. 2 peaks only you see. Compulsory make this a step. Okay, then you say okay. Okay, now this is the thing what you should know. Okay, once you do this, okay, now solution, now you say solve, current LS you do. You just see solution, solve current LS, take some time to solve. Okay, just wait. The solution is done, must be obtained. Solution is done, is obtained. That means we are more or less okay. We must get the answers. Okay, file, close you do. Now you see here, now so far you are operating general post process. Now time history post process you go. Time history post process, you click on that. Okay, there variable viewer. Here frequency 1 to 100. Okay, now here you click on add data button. Add data button you click. Okay, under that DOF solution you take. Y component of displacement you take, that is how it, that is Y component of displacement, I tell you, Y component of displacement, you say okay, see here, bring it down, here Y component of displacement, because of the force, no, Y component of displacement will be actually the amplitude, okay, amplitude of vibration for different frequency range, 0 to 100 we will observe, I'll give that and I'll just say okay. Okay, now once you do this, you clearly know it is Y component of displacement will be minus 4.7 to maximum this. Okay, once you do this, you see the list here. Once you see the list here, you see here, frequency 1, 2, 3, up to 100 I have done. Can you follow? Up to 100 I have done. Because I have given frequency range 1 to 100, number of substeps 100. That means 1, 2, 3, 4 only that. See here, amplitude is minimum, minimum, minimum. Once you go at 8, you have 4.7. Your peak has occurred. Okay, the maximum. Then again, the amplitude of vibration is very less and all that, very less and all that. You see here, very less. Again, the dangerous frequency is around 52. You see here, at 52, 0.4622, it's again a dangerous frequency. The peak has occurred. Okay, this is what you are supposed to know. Now, here you have an option called graph data. You just put the graph data. Okay. Put the graph data. Now you can see clearly the 2 peaks being shown here. Can you understand? 2 peaks, one at almost 8.2, another 52. This is the thing what you have to observe. This is the essence of the harmonic analysis, and you can change the axis also by plot controls, that is style, axis and all that. I show you in another problem where you can change the axis, but for the examination purpose and all that, you come till this stage and stop. The y-axis can always be changed. Now it is normal axis. You can make it logarithmic also in the later stages. Okay, I'll show you all that. Now this completes the session 2 on harmonic analysis. Thank you friends. Thank you very much for viewing. Thank you.